Well, good morning, everyone. Thank you, everyone, for joining and being with us here today. My name is Gregory Ormsby Maury. I'm the Outreach Coordinator with the Center for Agroforestry at the University of Missouri. This is the Agroforestry in Action webinar series, held monthly. Our guest today is Dr. Tom Sauer. Tom is a native of Minnesota, and he joined the USDA Agricultural Research Service in 1993, returned to the USDA in 1999, and he's currently working at the National Laboratory for Agriculture and the Environment. Dr. Sauer is a distinguished scientist. He's been very prolific with a long history of publications. He was awarded a Fulbright scholarship to study in New Zealand, a research fellowship from the OECD to conduct research in Italy at the Institute for Advanced Studies. He was elected Fellow of the Soil Science Society of America in 2012. He currently serves as the program chair for the Soil the Soil and Water Management and Conservation Division of the Soil Society of America. Tom's research, his research program is focused on the effects of tillage, crop residue, and manure management on energy, water, carbon, and trace gas fluxes in soil, plant, and atmosphere systems. Current projects include measurement of carbon dioxide fluxes from soil atmosphere, concentration gradients, development of a crop residue water content sensor, a variety of research topics, and also carbon and nutrient cycling in agroforestry systems. And that's, I think, some of what Tom will be talking about today with us. And his presentation is entitled Agroforestry for Climate Change Adaptation. Tom's presentation will run about 45 minutes, and then we'll have about 10 or 15 minutes for some question and answers. So please join me, and let us welcome Tom Sauer.
Thanks, Gregory,
There you go.
for the introduction, and greetings to everyone. It's a pleasure to visit with you today about agroforestry, and thanks to the Center for Agroforestry for giving me this opportunity. Agroforestry and climate change are pretty broad topics, so I plan to narrow things down quite a bit. We're going to talk about adaptation in particular, but also narrowing the agricultural aspects to a focus on food security. And in that regard, in terms of climate change and food security, we're going to focus in on the aspects regarding water, particularly crop water availability. We're not going to talk about mitigation, but as many of you may know and appreciate, agroforestry also offers opportunity for climate change mitigation, but perhaps some other time, some other day. With regard to food security, currently we have about 900 million, or 15% of the global population is malnourished or starving, with projections for a global population of 9 billion by 2050. So the concern in USDA and elsewhere is how are we going to meet that demand for food security? This graphic shows that we will need to produce more calories of food in the next 50 years than were produced and consumed in the last 500 years. So that kind of puts into perspective the daunting challenge that we're facing in food security. Now we're going to grow that food on our soil resources and our other associated natural resources, and we already know that many of our productive soils have already suffered some form of degradation. As a soil scientist by training, it's great when Science Magazine devotes an article to your resource. However, it's not so great when the focus of the article is all the degradation that has occurred globally. So there are climate constraints on productivity, physical and chemical constraints, and many of those are from man's activities, how we've used and abused our soils in a variety of ways. In North America, especially in the Midwest, we have very productive soils. However, they have been degraded primarily due to water and to a lesser degree wind erosion. So even here, in a very productive part of the world, we have constraints on productivity that are continuing due to degradation. Another aspect of global food security is this competition for land use. In the United States, we have a policy and programs in place for renewable fuel production. And this graphic in the lower right is perhaps a couple of years out of date because I believe now that red line is above the blue. And actually, we consume more of our corn grain for ethanol production than any of the other uses. So there's a tension here as well, and it's policy-driven, economic-driven by what we're going to use the land for, what we're going to produce, and how we're going to use the products of the land. And then we introduce into the picture climate change. And there are particular components that I would like to focus on. One is the general shifts, and again, keeping a focus on water, the shifts in precipitation. And it's not necessarily all about sort of annual averages, as these projections show, but it's in particular the perhaps seasonal shifts in the precipitation patterns. In particular, quite concerned are recurring model predictions that we will have less growing season rainfall in large productive agricultural regions of the U.S., Great Plains, parts of the Midwest, and the Pacific Northwest. Obviously, a big concern if we have a 20 or 30% reduction in growing season rainfall, what effects that might have on ag production. Next is the climate variability in terms of the frequency of extreme events. In 2010, Ames, Iowa had our third 250-year flood in 20 years. That's the basketball arena at the university underwater again. Just 2 years later, in 2012, we suffered the worst drought of my lifetime in central Iowa. So many predictions are that we will have greater frequency of these extreme events. And it's not only the frequency, it's the severity. Many people in production agriculture will take a figure like this and tell me, well, I don't know why you're concerned about food security. Look at the dramatic gains in corn grain yield following World War II that we've achieved in the United States. However, as 2012 demonstrated, we are still, even in this highly industrialized agricultural system, vulnerable to the extremes of these climate events. The drought of 2012 really drove home the kind of vulnerability that even these systems have. So I want to take a little break here, and because the discussion about climate change often focuses on sort of political views and priorities and economics, but I wanted to sort of put this into perspective of what really our choices are. And so a familiar image to many people is the story of the Titanic. The ship had warnings. They were told that there were icebergs ahead. Now the thing about icebergs are 90% of the iceberg is below water. So even though if you could see an iceberg, you don't really know what it looks like below the waterline. This is like climate change. We see it out there, but we don't really know what the full effects might be yet. So you're the captain. Let's take a few moments and say, well, we're the captain of the ship. What are our choices? Well, the choice of the captain of the Titanic, and by the way, the name of our ship is the SS Food Security. We're going to make the decisions about how we're going to address our food security issues. The captain of the Titanic basically said, steady as she goes, which I've characterized as the careless or the foolish approach. So, I guess the hope there is that maybe the iceberg will melt or drift out of the way. The thinking here for climate change is that maybe those effects won't be so bad and we'll be okay. careless or foolish thinking, in my opinion. The second choice is, well, let's just adjust course now. And I've characterized this as well-meaning because this might be an emotional response. Let's say, well, we don't really understand climate change. We're concerned about it, so we're just going to make some changes in our food security, our ag production systems now. Maybe a more gradual change over a longer time, but we may also be going into uncharted water. So if we make these decisions non-science-based, more in an emotional response, then actually we're still introducing uncertainty into those systems in the future. And if we don't understand more about climate change, in fact, we could sail right into the iceberg, so to speak. And in all cases, we have to keep in mind that we're taking on more passengers all the time. As the global population grows, the needs for food security continue to evolve. A third choice would be evasive action, which I have characterized as the reckless course. That is, we're just going to sail on ahead until we have absolutely bulletproof data showing what the effects are, and then we'll make some adjustments in our systems. Unfortunately, big ships like agriculture work best when they aren't asked to change dramatically and quickly. So we're looking for a last-minute change in course. It's a very risky proposition, in my opinion. And the consequences for waiting, deferring those costs, deferring those changes to future generations are that we could put them in a very serious situation, just because we chose not to make changes when we had the opportunity to do so. And lastly, and I'm hoping to convince people today that this is the best course to take, what I call the informed and prudent course. It's improve your ship and get better data on icebergs. So we know there are already problems in our food security system. I've already mentioned erosion, different forms of soil degradation. We can address those today, and those will help improve our food security for the future. We know that we also need to know more about what the potential climate change effects. So further investment in understanding climate change effects and investments in improving our resiliency of our agricultural systems, those will all pay off in making better decisions and thinking about course changes down the road, because this is going to have to be an iterative system where we're going to be looking at making changes as we go, adjusting course along the way if we're going to deal with the effects of climate change. The difference between number 4 and number 2 is really that we're talking about science-based decisions, trying to take the politics out of these decisions, understanding the economic, the social, all the other implications, because climate change is a very complicated issue, of course. And I'm just focusing on food security for the discussion today. So, back to agroforestry. How does agroforestry fit into the climate change discussion? Well, I think it actually offers some terrific opportunities, and a lot of discussions about climate change can become kind of negative, and I'm not negative. I want to think positively. We have some great challenges out there, but let's think about how we can address them, and I think agroforestry systems offer great opportunities to do so. If you're not familiar with the agroforestry topic, there are generally 5 systems that we talk about: alley cropping, riparian buffers, field windbreaks, forest farming, and silvopasture. All of these involve trees integrated with cropping systems, livestock production systems, together as a system. And why are agroforestry systems so attractive in terms of an adaptation practice? Well, first, they inherently provide multi-use potential. So if you want food production, but you're also interested in renewable energy, agroforestry practices offer opportunities to do that on the same land. They're suitable for some of our best lands or even marginal lands. So they are flexible practices. They're very flexible to different needs, different opportunities, climate, and soil resources. Likewise, they're very adaptable. They're living systems. We can manage them to enhance or achieve particular goals, and those goals may evolve over time with the life of the system. And they're restorative. They tend to do a good job of protecting soil resources, water resources, air resources. So they can take degraded lands, degraded water resources, and restore them to higher level functioning, improve their quality. So the situation that we find ourselves in is that we need significant increases in productivity for food, fuel, feed, and fiber, but we also must do this in a way that's not going to further degrade our natural resources. The FAO, the Food and Agriculture Organization of the United Nations, has this term sustainable intensification, and I really like it, and I think agroforestry is a great fit for the idea of sustainable intensification, which is optimizing crop production per unit area, but also taking in the sustainability aspects, and those are very broad in terms of social, political, economic, and the environmental impacts. It's interesting to me that in North America, where we have this production agricultural system really based on monocultures of particular crops in large areas, that our agriculture after European settlement really was, in a way, agroforestry. It seems a novel idea to many growers now, but in essence, for much of the early history of our country, we really practiced agroforestry. European settlers came to the East Coast, and it was a forested region. They observed how the Native Americans grew their food, and a lot of examples. So this is a field in Virginia where they planted in the Native American style, where they cleared with fire or by hand the underbrush, the understory, burned it to release some of the nutrients, and then they're growing their crops underneath these tall trees in the gallery. What's interesting is that when the settlers came to the treeless plains, they didn't know how to, they hesitated because they didn't know how to deal with growing crops in these prairie or grassland areas. They were more familiar with growing crops around trees. So we've kind of come full circle here. Now we're trying to go back to the point of saying, well, trees and crops can be grown together, and that's what agroforestry is about. My colleague Kay Stichter in Africa sent me a couple of photos from examples from the region that he's familiar with. In this particular case, it's from Tanzania. Here they're using trees to modify the climate, as the Native Americans did in eastern United States. In this case, it's coffee growing under what he calls the umbrella shade trees. Now, it's interesting that the extension in Tanzania were encouraging the growers to remove the trees, but the growers felt that the trees were very effective in protecting their crop from dangerous vertical winds due to rain showers on the slopes of the mountain. So Case showed me that they actually went and made some measurements to understand what was happening in this area, and he made a very succinct conclusion there that our wind measurements proved that the farmers were right. So for the same reason that we plant trees around our homes, they offer the opportunity to change the climate and protect structures, crops beneath them from the dangerous effects of high winds, and also to improve or moderate the climate extremes. So, trees with crops. Some of the advantages there on the left. You have multi-tiered rooting systems. These are also due to the fact that you have perennials mixed with annuals, and different growth habits with the season allow the different species to exploit different root volumes. This leads to enhanced nutrient cycling. I've already mentioned that you can create a favorable microclimate for the species beneath the tree overstory. We're not disturbing the soil, so we tend to increase the amount of soil organic matter. We have the opportunity to harvest multiple products from the system. Could be all of the food, feed, fiber, production can all be from the same area. And then additional ecosystem services. In particular, recent discussions a lot about pollinator habitat. Of course, it's not always positive. There are concerns that you have when you introduce trees into cropping systems. The trees can shade the understory species and reduce the productivity. There can be competition for water or nutrients, and the same species that may provide pollinator habitat may inadvertently provide habitat for non-beneficial species. And the effects of the trees on local microclimate are complex. So, from a climate change adaptation approach, the challenge is to design and manage these systems to reduce the negative effects and enhance the positive ones. So, getting back to the image with option number 4 for the Titanic, we're talking about science-based decisions here that we can use to design and manage systems for particular objectives in terms of climate change adaptation. I've trained in micrometeorology, so I apologize for using an equation, but it seems almost a prerequisite in my career that I have to have at least one equation in every presentation. The surface energy balance equation, on the left-hand side, we have the available energy. It's the net radiation minus the soil heat flux. And when we talk about global warming, if we use that term, the atmosphere is warming, the surface is warming, so our available energy tends to be increasing. We're not talking tremendous amounts here. There's more variation with latitude, for instance, on the globe than there is due to climate change effects. But they are increasing. The available or the turbulent fluxes on the right-hand side of the equation, that's where that energy goes. And it goes really in two places. Lambda E, the latent heat flux, is just evaporation. It's the energy used to evaporate water. On the right-hand side there, in purple, that evaporation can be the transpiration from your trees, your crop, or evaporation directly from the soil surface. Any other energy that's not used in evaporation is used for sensible heat. That is warming of the surface. So there's a complex interplay in the surface energy balance between the available energy and the turbulent fluxes. And that determines how much heating we have at the surface, how much the soil warms, and how much evaporation we have. In a complicated way, and I'm going to just show in the next figure a data figure to try and simplify this whole complex surface energy balance in a way that's meaningful for our discussion today. This is a figure of a week of sunny days in northwest Arkansas over a pasture. The top figure here, the top curve, is the net radiation that's driving the system. Down here, the small one is the soil heat flux, the smallest flux. But what happens, we had all these sunny days after a rainfall, and notice that the latent heat flux curve decreases every day in this beautiful, nice linear pattern. That's because the soil is drying out. As we know from the previous slide in the surface energy balance, the only other place for that energy to go is for surface warming. So there's this interplay between evapotranspiration and sensible heat flux of the surface warming. This is an important feature when we're trying to design systems to enhance agricultural productivity, because water use and yield are intimately related. The figure on the left the dates or the numbers by the symbols are the dates the data was collected. And those aren't from this century. Those are from last century. So some of these data points are over 100 years old. This term down here on the x-axis, this is transpiration, water use by the plant, and this is yield and dry matter. So you see a nice linear relationship between transpiration and yield. And I can show data from recent years. It shows the same concept, this linear relationship between transpiration and yield. And it all means that if you want to attain higher yield, it's going to take more water. And our water use efficiency, as it's often called, is fairly specific to crop and region. So it's not something that we can easily change. So if we want to obtain higher yields to meet our food security goals, we're going to need to provide more PAW, the plant available water. So I ask the question here, is plant available water becoming a yield limiting factor in rain-fed agriculture? We do a good job of pest control, providing nutrition, all of these improved genetics in many of our crops. Is it going to come down to the fact that we need more water to obtain higher yields? The link between the energy balance and the water balance for the surface is right here with evapotranspiration. So when precipitation falls on the surface, there's two routes that it can follow. It can run off on the surface, or it can infiltrate into the soil. We like to enhance that infiltration into the soil because when we store water in the root zone, we make it available for evapotranspiration, and that enhanced amount of soil water is not going to be a limiting factor to achieving our yield goals. There are also consequences for if we have excessive runoff. Practices that increase runoff can lead to excessive stream flow and pollution and flooding that we've seen recently in Iowa. So there's a lot of discussion about techniques to limit runoff, improve infiltration, and especially enhance soil water storage in the root zone to help us achieve higher yield goals. Well, how do we store more plant available water in the root zone? One of the best ways to do that is to try and restore our soil organic matter levels, because soil organic matter is very critical factor in enhancing water storage in the root zone. Soils that are high in organic matter tend to have better structure and do a better job of retaining water in the root zone. When we cultivate soils, destroy that structure, mineralize our organic matter, we tend to reduce the water holding capacity of the soils. So that's another form of soil degradation, another trend that we need to reverse if we're going to build more resilient agricultural production systems. Right, getting back to agroforestry again. Well, what does this mean, this management of water in terms of agroforestry practices? I'm going to spend quite a bit of time now talking about tree windbreaks, the field windbreaks. And these are particularly well adapted to drier cropping regions approaching semi-arid conditions. This figure does a nice job of illustrating the effects of a tree windbreak on local microclimate. We imagine there are trees in this line here. The wind is blowing from the left to the right, and this line represents anything above the line is an increase, anything below the line is a decrease. So by the presence of trees in a field, we have a significant decrease in wind speed. So as the wind slows, the relative humidity, air temperature, and soil temperature increase because of this protected zone behind the trees. What that does is it also effectively decouples the atmosphere behind the trees from the atmosphere above, so evaporation is decreased. And the only thing I don't like about this figure is that it shows crop yield increasing close to the shelter, when in fact, crop yield is more likely to decrease and then increase as you get farther away from the shelter. So there are complicated microclimate effects, but these have been shown, tested, and observed many times. And the net result is that we have seen climate modification at the field scale due to the tree windbreaks in a variety of climates and cropping systems. That end result is that on average, and these are a couple of reviews, one by Newberg, and he cited a previous study by Court, that there is on average about a 15% increase in crop yield, and that's a field average, when you have sheltered versus unsheltered fields in these regions. And this data is from Australia, Canada, and the US. Well, unlike many climate change adaptation practices, agroforestry, I think, already has a success story. And this came from a long-term drought in the 1930s in the Great Plains of the United States, the so-called Dust Bowl. The federal government was searching for a way to address the Dust Bowl conditions. And they had a study produced by the U.S. Forest Service, and it was a feasibility study about the opportunities and the possibilities of planting trees in the Dust Bowl region. The title of the study was called Possibilities of Shelter Belt Planting in the Plains Region, a study of tree planting for protective and ameliorative purposes. The idea here was to take this Dust Bowl region and plant tree windbreaks in it to reduce the effects of the persistent drought in the region. So they chose this shelter belt zone from Canada down to the state of Texas. It's 100 miles wide and 1,150 miles long. They did, in this feasibility analysis, chose which soils, which trees. They did a very thorough study of groundwater, native vegetation, and convinced the federal government, in particular convinced the President of the United States, to go ahead with this plan. The project was called the Prairie States Forestry Project. It ran from 1935 to 1942. They found that 56% of the area within that shelter belt zone was suitable for tree planting, and they planted 217 million trees, over 18,000 miles of windbreaks, covering 238,000 acres. The figure on the right is from a study by Reed, published in 1958, where they went back and looked at the trees that were actually planted in the shelter belt zone, and they found that 73% were in fair to excellent condition. So most people feel that this project was a great success. Well, how do we judge success in a project like this? Well, I judge success in a variety of ways. In this case, it's difficult to estimate, but I think about 40% of the original plantings are still there. In fact, I've been in some of the original plantings and have done some research in them. But perhaps even more important is that around those original plantings, there are other newer plantings, and it's a practice that is still being used. So obviously, the growers, landowners of these states realize the potential benefits of the tree windbreaks, and even after the windbreaks, perhaps the trees died or land ownership changed or land use changed, they continue to use these practices in the region. So I think that itself is a testimonial to the fact that the project was a success, and that the practices worked to alleviate the effects of this persistent drought. Interestingly, there's a lot of political and social background to the Prairie States Forestry Project. And it's interesting because as we discuss potential climate change adaptation practices now, you see some of the same sort of political divisions and reluctance by agencies, insistence on more information, all of these things coming to the front. And it's just like what happened during the Prairie States Forestry Project. It was a high priority to President Roosevelt, and I think that's one of the key factors, is that this project had support at the very highest levels of government. FDR would refer to it as my baby, and people in the program referred to the plantings as FDR's trees. Project leaders reported directly to the Secretary of Agriculture, and the Secretary of Agriculture to the President of the United States. It was bold and innovative. People at all levels in the Forest Service took a lot of risk in supporting and administering this program. It was responsive. From inception, approval of the project, they started planting trees within 8 months. It also had a top-down and bottom-up management style. Not only were the instructions coming from Washington, but very often changes which occurred on the fly were coming from the field. So people in the field were saying, this doesn't work. And they were making changes to make it work. And it wasn't a rigid, structured project. And the basis, and really important, is that it was very well researched. There was a very holistic perspective. Carlos Bates and Raphael Zahn were the two key researchers behind the project who did a very thorough job of vetting different ideas, different approaches, and making sound, science-based decisions that led to the success of this project. Raphael Zahn, who's one of the key architects, is considered the dean of American foresters. And just to show a couple of examples of the different ideas they had in mind, at one time they were talking about planting a north-south windbreak every mile across the entire shelter belt region. And this was an artist's conception of what that would have looked like. And here you can see another picture of different drawings on this map in the shelter belt zone that were being considered at the time. So you might ask, well, where did Zahn get this idea? Well, Zahn was a Russian. He was born in Russia, immigrated to the United States, and he knew of the work of a scientist named Dukachayev at Kamenaya Steppe in Russia. The Dukachev plan, basically the steppes of Russia were prone to drought, and so Dukachev was sent there to try and reduce the droughts and reduce the famines that were plaguing the region. Dukachayev, who is also known as the father of modern soil science, took an approach that the important thing was to capture and store precipitation for crop growth. And his approach included several components that included trees, including tree windbreaks, which interestingly, the Kamenaya data show about the same 15% increase in yield across field average. It was conserving moisture by reducing evapotranspiration, physical protection from Socovies, which were hot, dry winds, and capturing snow in the winter. But he went beyond windbreaks. They had riparian plantings along streams and gullies, and this was a practice that was widely adopted. And in fact, visiting Russia in 2012, they are still putting windbreaks in. It's one of those practices that has survived the breakup of the Soviet Union. They are just like in the Great Plains of the U.S., viewed as a successful field management practice. It came to be so successful, in fact, that at one point, the Soviet Union had grand designs, and this map shows all the plantings that they were going to have over European Russia to essentially change the climate of the region. And there's Comrade Stalin looking at the map, and the caption says, "And we will defeat the drought." So following along the same line, there's always been this question about scaling up and the effect of trees on microclimate, not only at the field scale, but perhaps at the larger scale. Zahn, in fact, published a report in 1927 called Forests and Water in the Light of Scientific Investigation. It was published in the Forest Service, but was very controversial. For that second item outlined in red, forests increase both the abundance and frequency of precipitation up to 25%. Many people feel that deforestation will decrease rainfall and create hotter, drier conditions. However, it's always been more controversial to reverse that and say that if you plant trees, you will change the climate in the image that Comrade Stalin had in mind. So this became a real issue with regard to the Prairie States Forestry Project. And that picture of me is actually standing at Kamenaya Steppe in one of those windbreaks planted shortly after Dukachayev's time. And this is an area of less than 500 millimeters of rainfall, and yet you see a very healthy, thriving forest in this area. The paper reference at the bottom, Van Dyke and Keenan, said the historically popular assumption that forests generate rainfall may have been dismissed too readily by science. So just in the last few years, interestingly, this topic has come back. And so now we're talking about climate modification at a local or regional scale with trees. And there are already a couple of examples under play. The 3 North Shelter Belt program in China, it's a very long-term, beginning in 1978, planned to go until 2050, 35 million hectares of shelter belt forests, where they're actually farming within some of the tree rows, and this is a very arid region, some places 200 millimeters or less rainfall. The article by Liu et al. At the bottom there, looking at modeled precipitation in the region, their estimates are that the planting of these trees is indeed going to increase precipitation by 20%. Again, very controversial about whether or not afforestation practices like this are going to have a regional effect on climate. Another modification is the Great Green Wall in Africa. This is primarily addressed at desertification to slow the advance of desertification south into Africa. It's a 15-kilometer wide strip, 7,000 kilometers long from Dakar to Djibouti. And perhaps you know, the Nobel Prize laureate Wangari Maathai was instrumental in tree planting programs in Africa and was one of the founders of this Great Green Wall movement. So that's a lot of information in a short period of time. I just want to end with some information here about USDA efforts. The USDA has created some climate hubs to help deal with this dissemination of information. One of them is hosted by our laboratory here in Ames, Iowa. They are supervised through the Office of the Chief Economist. So the idea behind these climate hubs is the dissemination of information from researchers through the climate hub down through our tech transfer agencies to stakeholder groups, farmer ranchers. So it's an information flow in both directions, however. So we have research going to producers, and we take these questions and feedback back through the Climate Hub to the research arms of USDA and other federal agencies. So agroforestry actually is on the agenda. These climate hubs are Forest Service or Ag Research Service leads, so definitely climate change and agroforestry are on the agenda in these climate hubs. A second important thing to note is that there is a report coming out on agroforestry and climate change. This will be produced by the Forest Service, released in early 2016. and it's agroforestry's potential as a climate-smart strategy to build productive, resilient U.S. agriculture and lands. There's contact information here, Michelle Schoenberger and Gary Bentrup at the Forest Service's National Agroforestry Center. If you have questions or you'd like more information about this publication. And lastly, I've been involved with a couple of efforts about, we talk about all this science and all this information. We're trying to do work with this agroforestry report, the climate hubs, to make this understandable and to the general public, to our stakeholders, the farmers, producers. But what really it comes down to is making decisions as a society. And I go back to Jared Diamond's book, Collapse, How Societies Choose to Fail or Succeed. And the book is all about environmental threats and how societies respond to them. And the most common failure was that they failed to solve a problem, even one that they recognized that was a danger to them. The critical choices to enable success, however, Diamond recognized were a willingness to reconsider core values and to engage in long-term planning. The Prairie States Forestry Project actually is an example of a success. The core value that was reconsidered, it was the first time the Federal Forest Service ever had worked on private land. And it was hugely controversial at the time that the Forest Service was going to work on private land. And second, to engage in long-term planning, one of the biggest criticisms of the project was it will take too long for the trees to grow. That other practices that were going to take effect more quickly should be preferred. So the Prairie States Forestry Project provides an example, a strategy to succeed, and how we overcame those in that particular case. And I think climate change is winning strategies for practices are going to have to overcome the same problems if they're going to be successful as an adaptation practice in the future. We actually held a conference talking about some of these sociological aspects of decision making, including environmental ethicists. Philosophers were involved in these discussions about how we value, what things we value, how we value them, and how we make decisions about, at a society level, about how we're going to address climate change in the future. And I also want to mention that agroforestry, definitely the topic of our discussion today, but in order to build resilient agricultural production systems, there are many other practices. Most of these are also very compatible with agroforestry, but agroforestry is not going to be the only adaptation tool that we're going to use as we go ahead in adapting to climate change. So I see I'm out of time, and it's time to finish up. So just to review, climate variability is going to result in increasing challenges for agriculture. We're already seeing some of those effects, and not only in production but in the economics, the costs associated with crop losses due to flood and drought, becoming very serious issues at a national and global level. Sustainable intensification of land use is needed to meet our production demands, but we have to prevent further degradation of our natural resources. Agroforestry practices offer excellent climate adaptation and mitigation potential. I know we didn't talk about that much today, but the opportunities to modify local climate and change the surface hydrology are key factors that will be useful as an adaptation tool. We already have sufficient knowledge of agroforestry benefits to encourage adoption, so we can't use the excuse that we need more data before we can move forward. I think we have sufficient information based on past history and practices, Dust Bowl era prairie states forestry project, for instance. But we do need more work on what the potential climate change effects are and fine-tuning these practices for our future agricultural production. And with that, my time is up. I thank you very much again for the opportunity today, and I think Greg is going to see if we can address any questions at this time.
Well, Tom, thank you very much. I think that was an excellent presentation. Yes, I think we'll have some time for some questions, and I'm going to drag out a question box here. It's really quite stimulating, interesting there to see the example of the Prairie States Forestry Project and as a successful example, and I guess what can be done when the conditions allow it or there's political will. So yes, I've just dragged the question and answer box into the presentation window, and participants should be able to type in some questions. And so while we're waiting for that to come in, again, I thought that was a really excellent presentation, giving an overview of from the this kind of science and research that you're working on, and tying that to several levels and what potential contribution of agroforestry systems, and then some of these examples of some of these very ambitious, major scale, multi-year projects to try to use agroforestry approaches for influencing microclimates and adaptation to climate change. Certainly hope that future generations are not going to look back at our generation as having failed to even try to solve the problems. But, hopefully we have some questions coming in here. Please, if you type your questions in the, can everyone see the question and, whoops, sorry about that. Can everyone see the question and answer box that's there? Is that visible to everyone? Yes, everyone please who participated, yes, do know that we have recorded the presentation, and it should be posted on our Agroforestry in Action website. That's agroforestryiinaction.org, where you can see a schedule of upcoming webinars and previously recorded webinars, including this one. So if you can see the question and answer box, do please type your questions in the dialog box that you'll see at the bottom of the question and answer. I do see one question coming from Jerry Neal that's in the chat box there, and she asks, is there a key question or bit of information that would help clear up the mystery of whether or not more trees increase microclimate rainfall or not? Don, would you care to address that one while we hopefully wait for any additional questions?
Sure. That's a good question. It's a question that I ask my climate modeling colleagues all the time. And usually the answer I get back is it's a question of scale. Because when you think about the reverse, which is the deforestation effects, very often those are large areas. We're thinking Amazon rainforest, for instance. And so the observed decrease in rainfall as a result of that deforestation, they believe is largely due to the large area involved. Zahn's report, 1927 is a long time ago, but Zahn's report was pretty darn thorough, had looked at a lot of information, focused primarily on Europe, makes actually pretty convincing reading. Ironically, he was an impressive scientist. But we don't have an example to test this, because we've never had such a large-scale afforestation project. Now, the project in China is approaching this scale. As it continues to grow, and there's a modeling study that I referred to, it would be interesting if there's a point where they actually have observations that show this increase in rainfall. And of course, this is going to be complicated by the fact that as long as it took to plant such a large area of trees, the climate itself may have already changed in that region. So it's going to be difficult to get a definitive answer to that question, even in a case like that where we do have such a large scale, spatial scale afforestation project.
All right, thank you, Tom. I'm wondering, I don't see any questions appearing in the question and answer box. Are the participants able to see? Oh, here we go. Karen Vanna, can you see the question there, Tom? She asked, can you speak more
Yes,
to the
I can.
significance of restoring soil organic matter levels?
Yes, we've done a lot of research. In fact, we have an ongoing project in that area right now where we're looking at the effects of the tree windbreaks on soil organic matter, both in the windbreaks and in the adjacent, compared to the adjacent cropped fields, cropped or grazed. I think it's very important. In the Midwestern U.S., we've lost about 50% of our soil organic matter. And we have an active project going on looking at research methods to measure plant available water and the effects of soil organic matter. The data that we have so far, the published literature that we have, suggests that we could double the amount of plant available water by restoring the soils to the original organic matter content. Now, that sounds like a lot, and it's good. However, this is for topsoils which may be 30 centimeters deep. So it's complicated by the fact that it's also related to the structure of the soil. But the bottom line is, I believe firmly that if we were to restore some of that soil organic matter, improve the structures of the soil, essentially restore soil health, we will increase the amount of plant available water that we can store in the root zone.
Thank you, Tom. A few more questions have come in. I'm not sure if you can read the entire question from Marie Gosme, but so in the meantime, let's go with Dennis Bettenhausen's questions, and he asks, on a small scale, for example, 10 acres, how wide would the alleys need to be in alley cropping or some kind of agroforestry system?
Right. That depends on the crop you're growing and the tree species, of course. The alley cropping site that we have in Arkansas, the spacing between rows is 50 feet. And there are oak and pine, sycamore, cottonwood, and pecan at that site. So I think a 50-foot spacing is a reasonable starting point, but again, depends on your crop and your tree species.
Right. It does depend. If you're looking at a long-term with plantings such as pecans and growing those for timber nuts, a wide spacing like 50 or 60 feet is probably what you want to shoot for. But again, depends on many factors, as Tom was mentioning. And we're happy to engage with you, Dennis, here at the Center of Agroforestry to look more specifically at any system you might be looking to design and implement. Moving on to another question, Tom, I'm not sure if you can see the full text. If you hover and select over Marie Gosme's question, you'll see the full text, but she's asking, complimenting on you in the presentation, and she mentions that she works on cereal yields. And she's asking if you think there's any opportunities for payment for ecosystem services for these types of agroforestry practices, and then, or can it only be developed through government initiatives?
Yeah,
maybe
that's
referring
also
to some of the larger scale. If you have a comment on that.
Well, at one time, USDA had an Office of Ecosystem Services and Benefits, and we were all very hopeful that we were going to see bundled ecosystem service packages, something like a carbon credit that were going to be linked together and used as incentives for growers. Now, that never materialized, and that kind of gets back to the discussion about soil organic matter. It's almost a shame that recent interest in climate change started with soil carbon sequestration and carbon credits, because when those programs failed to materialize, I think many growers concluded that soil organic matter must not be important then. And it wasn't that it wasn't important, it's just that these programs never happened. It is very important. And the associated ecosystem services with soil organic matter in terms of water quality, enhancing crop yield, reducing non-point source pollution by increasing infiltration. These are all terrific things and terrific benefits to society. How do we encourage adoption? Do there have to be payments? That's been the standard approach in American agriculture recently, and it's been through government initiatives. There is some discussion, and I've had some personal discussion with individuals who are talking about private corporations initiatives. In essence, these are companies that want to be perceived and want to be more green, and so they're interested in investing in practices themselves outside of government programs that they feel sort of meet their criteria for sustainability, for instance, and or addressing climate change issues. So interestingly, just in the last perhaps 3 years, we've heard several discussions by large private corporations with significant resources who are looking for practices. And I think agroforestry, and that was my discussion with one of these individuals, was about agroforestry as a potential practice that their corporation could support.
Okay, very good. Well, thank you, Tom. I think I don't see any additional questions there, and we've now past 12 o'clock, and I think many of our participants may need to get on to other engagements. So I think with that, we're going to conclude our presentation. I want to thank you, Tom, very much for an excellent presentation, and thanks to everyone for your participation. Thank you, Tom.
All right. You're welcome, and thank you.
And so that concludes this month's Agroforestry in Action webinar. Please join us next month for a presentation on silvopasture in the Northeast United States by Joe Orefice. And do please check our website, agroforestryinaction.org, for information on upcoming webinars. Thank you so much.